Questions about anything? There's no class on Monday. And then homework 1 is due Thursday night next week at 11:30 p.m. Well, today I'm going to get rolling talking about the basic subject matter of the course, which is going to be complex differentiable functions on open sets in the complex plane that are connected. And so I need to make some definitions before I can really start getting into it. So there's two kinds of connected, or two main kinds. One concept is path connected, and if you took a class in topology or maybe analysis, there's another definition of connected involving open sets. And you have two open sets that cover a domain, a region, and they're disjoint. Then either one has to be the whole set, or the other one has to be the whole set. That's the fancier definition of connected. For an open set, those turn out to be the same. So for us, an open set in a complex plane is going to be connected, meaning path connected. And here's a picture. Here's a blob in the plane. It can have holes, but being connected means give me 2 points in there. Here's a Z1, and here's a Z2. Then there's a continuous curve that connects the two, like that, completely contained in the region, in the open set. So the open set here doesn't include the blue line, but it's the shaded stuff inside. So that's an open set. And you know that when you have a continuous curve like that, I could approximate that curve and stay in the open set. So I like to call my open sets omega. There's an open set. Okay, those 2 points are connected by a continuous curve. Because the thing is open, I could take this polygonal path, staying in. I'd have to make maybe it. Let's see, that's going to be really close, etc. So a thing to note is that we could change the definition to mean a piecewise C1 curve. In fact, that's piecewise linear. So in fact, omega, we can assume that the curve is piecewise C1. I like to call my curves gamma. Gamma connecting Z1 to Z2 in omega is C1 smooth. So it can have corners piecewise C1 smooth. I'll write out a more careful definition of piecewise C1 smooth soon when we study complex integration. But it just means that it can have corners and the derivative exists and it's continuous except at the corners where it jumps. And in fact, in this picture here, those chords are piecewise linear. Questions about that? Yeah.
C1 smooth?
What?
C1 smooth?
C1 smooth, yeah.
Okay.
Looks like E1, but it's C1. Okay, So the basic objects that we're going to study are functions on a special kind of thing called a domain. Omega is a domain. Some books use the word region. If it is open and connected. And by connected, I mean path connected. So I'll put path in. It's a theorem in topology that in the complex plane, on an open set, path connected and connected are the same thing. So I don't have to be picky about how I define it. It's a fun thing to check that out when you take a topology class. Okay, so we're going to study functions on that kind of a thing. Let's see, I'll show you why being a domain is kind of an important thing. So here's a little lemma that we'll want to think about. Let's suppose u of xy is continuously differentiable on a domain. Domain omega. And it has a zero gradient. And the gradient of u is identically zero on omega. Then, because the thing is connected, u has to be constant. Okay, and the proof's pretty straightforward. By the way, I'm identifying with, R2 with C when I talk about these sets. And u of xy is a function of, it's a real function of x and y. So the proof is very straightforward. If you integrate along gamma, let's say this gamma is piecewise C1. If you integrate gradient u dot ds like you did in sophomore calculus, that's equal to u at the right endpoint minus u at the start. To u at the end minus u at the start. Okay, and it's important that gamma be piecewise C1 to make sense of this. And u needs to be continuously differentiable for that formula to be true. And so that would be a big fat 0. So these things are equal to 0. And so I can let the z2 move around and hold z1 fixed. And that would show me that the function is constant. So let's hold z1 fixed and move z2 around. That's how you see that. Okay, so that's an important consequence of being a domain. If I had two separate blobs that weren't connected, it could be one constant on one domain and a different constant on the other. So, and there's some simple facts that I won't dwell on, but I should mention at least. If you haven't seen this stuff before, I defined open sets last time, and simple facts are things like if omega 1 and omega 2 are open, Then, of course, their union is open. And so is their intersection. And it's a pretty simple exercise to prove that from the definition. Let's see, the intersection one, union one's kind of trivial. The intersection one is maybe more interesting, because when you pick a point in the intersection, then you know it's omega 1 is open, so there's a disk of radius r1 about that point in omega 1. And omega 2 is open, so it'd be a disk of radius r2 about that same point. And you realize, oh, if I take the minimum of those r1 and r2, then they'd be in both of those. And that would show you that the thing is open. Did I see a question?
I think you just explained it, I think.
Yeah. Anyway, I'll leave that as something you should think about. I think some of the exercises dwell on things like that. Interesting. If I have infinitely many, so omega j open, then the union of infinitely many is open, but the intersection might not be if you have infinitely many. So it's, when you have finitely many, then of course you can take the minimum of those r's. But if you have infinitely many, the minimum of those r's might be 0. So it's very easy to come up with an example, say in the real line, of intervals that shrink down to nothing. Like the open intervals from 0 to 1 over n, and take the intersections of those, that would be empty. Okay, let's see, a couple more words I need to define. The boundary of a set. So a point z naught is a boundary point of a set in the complex plane if for every epsilon bigger than 0, no matter how small, d epsilon about z naught contains a point in S and outside of S. Okay, so when you think about some of those pictures I've been drawing, let's see, maybe I have a circle where this circle would be part of the set for some of it, and maybe this dotted part is not part of the set, and the shaded region here is the inside. So the boundary point is exactly what you think about. If I put a dot here and put a little small circle around it, no matter how small, that circle has some points that are in the S and some points that aren't. And in this case, S contains that black boundary point. But over here, S doesn't contain that boundary point, but it's still a boundary point. I guess I should make it look like it fits the set. So those red dots are boundary points. And of course, you can get some pretty wild and crazy domains. One of my favorite wild and crazy domain is the Sierpinski snowflake. Is a domain in C. Let's see, how do you make the Sierpinski snowflake? You've probably seen it in a picture in a book. You take an equilateral triangle, then in the middle third of each of those you would take another equilateral triangle sitting on it, like that. And then at each spot where you can stick some more triangles, you stick a little equilateral triangle in the middle, like that. And you keep doing that. It's a really fascinating thing to think about. Has some interesting properties. This is going to get tedious in a minute, etc. A couple more and I'll be done. There. And you keep doing that. Whenever you can stick one on the outside, you stick a new one. And I'm filling in those lines that when I stick a new triangle on, I fill in the line that's where they connect. Okay. You can convince yourself that's an open set. You can also convince yourself that it's path connected. I could follow a path from the inside and keep going out and out and out until I get to any one of those points I want to get to. So it's path connected. It's a fascinating thing because it has finite area. It's the sum of the geometric series when you think about it, when you add up the areas. It's a finite area, but the boundary distance, but the length of the boundary curve is infinite. So there's a famous thing called the isoperimetric inequality that says that the circle has the smallest area possible for something of that area. And it shows that that isoperimetric inequality can get really bad because you can have a finite area and you can let the boundary, the perimeter, go to infinity if possible. And in this case, the perimeter is infinite. Anyway, we're going to prove something. We're going to prove the Riemann mapping theorem, or talk about the Riemann mapping theorem later in the course, which is going to say that that domain has an analytic, a complex differentiable map that maps that to the unit disk. It's going to turn out to be a conformal mapping, meaning it preserves angles. And it's just mind-blowing to think how you might come up with such a thing. Question? Does that have to be drawn with dotted edges or is it solid? Yeah, the open set is the stuff inside that. So you're right. So the boundary curve, I would make a dotted line if I wanted to emphasize that it's not in the set. So it's the interior of all those triangles that I stick together and fill in those lines where I glue one on. Okay, well that's topology. Enough topology for the moment. Now I'm going to shift gears and talk about calculus on C, which for a while will feel like it's nothing new. So let's see, if we're going to do calculus, we've got to talk about limits. The limit as z tends to z naught of a complex function f of z is a complex number L means okay, so like in freshman calculus, given an epsilon bigger than 0, there is a delta bigger than 0 such that f of z minus the limit L is less than epsilon when z minus z naught is less than delta and z is not equal to z naught. You know, when we're going to do difference quotients, and so in the difference quotient, when z is equal to z naught, that difference quotient doesn't make any sense. So the definition of limit, it's important that you don't include the point in the middle in this thing. That's why the z unequal to z naught is going to be important, because the function doesn't even have to be defined as z naught for the limit to exist. And if you look at that for about half a second, you realize, boy, that looks exactly like my freshman calculus book, except in the freshman calculus book, that thing is an absolute value, not the modulus. And the function, the z is a real number instead of a complex number, et cetera, et cetera. But that fact, let's see, so I guess the picture here is, draw the picture. Here's L. The disk of radius epsilon about L would look like this. And there's this delta thing, and so that's the delta thing is about z naught. This might be a really small disk, who knows? So that's radius delta. And what this definition means is that this shaded region gets mapped by F to something inside here. So a blob. And let's see, I better be careful. Z naught is not included in the picture here. So I punched that Z naught out. And I don't know where Z naught goes, but it might go to L, it might not go to L. But that's the picture of what that definition means in the complex plane. So obviously different than the real case, where those would be intervals instead of disks. And of course, it would be nice if Z naught went to L. And when it does, then there's a word for that. F is continuous. At Z naught, if the limit is what it's supposed to be. And of course, being continuous in an open set means it's continuous at each point. What? F of, yeah, that doesn't make any sense. F is continuous in an open set means it's continuous at every point in the open set. Okay, well, this observation that the symbols on the paper look exactly like the symbols on in your freshman calculus book leads to a simple fact. All the theorems you learned about limits in freshman calculus so all the rules about limits from freshman calculus go over to the complex case. So freshman calculus, R to R, carry over C to C. And not only that, but with exactly the same proofs. And even though the symbols mean different things, we have the same basic facts, like the triangle inequality. All those facts carry over, so that anything you do with the real numbers is valid for complex numbers. So maybe I'll put an exclamation point here. With the same proofs. So an example would be stuff like if the limit as z tends to z naught of f of z is equal to a, and the limit as z tends to z naught of g of z equals b, then the limit of the product exists and is a times b, stuff like that. And of course in freshman calculus you sat through the demonstrations of those things and were bored to death for a while, etc. And for example, the quotient one would be the same. And of course you have to say provided the denominator didn't tend to 0. Then you'd have the same rule. Maybe I should say that. And the limit as z goes to z naught of f of z over g of z would be a over b when b is unequal to 0. So I'd maybe provided that b is unequal to 0. Doesn't matter in the first one, the product. In the quotient, it does matter. Anyway, so a consequence of this is that complex polynomials are continuous. Let's see, so the y of that would be very simple. Let's see, we'd have an a naught plus a1 times z. A naught is continuous. A constant thing is continuous. That's the most trivial thing to check. And now here I've got a product of continuous things. A1 and z is continuous. They're both continuous. So the product rule would say that's continuous. By the way, when you're showing that z is continuous, the epsilon equals the delta. It's the easiest thing to do from the definition. The epsilon is the delta when you show that z is continuous. And of course now we can use the fact that the sum of two continuous things is continuous, etc. And the next time you'd have a2 times z squared, and z squared would be z times z. That's a product of continuous function, etc. See one more. A3 times Z cubed. This one, we just showed that Z squared is continuous, and so this is Z times Z squared, product of continuous things. So you can build up continuous functions by multiplication and addition, etc. Okay, so now the big moment is I'm going to start talking about real calculus here. Definition, F is complex differentiable. I like to say C differentiable. So I don't have to write complex. At Z naught, if the limit as Z tends to Z naught of the difference quotient, F of Z minus F of Z naught over Z minus Z naught exists. If it does, call that thing F prime of Z naught. If it does, call the limit F prime of Z naught. Or sometimes I might call it dF by dZ when Z is equal to Z naught. Stuff like the stuff you do in calculus. Well, the fact that we've just observed is anything you can do with limits in the real case carries over exactly in the complex case. So all the rules of differentiation R to R hold C to C. Question?
Is there easy proof to transfer every theorem real analysis all at once immediately to counterparts and complex analysis, or do you have to...
Yeah, go check out your book and say, okay, that X is now a Z. That's basically all you have to do. And when you look at the proofs, you realize, oh yeah, the triangle inequality holds the same. Everything's going to work. And of course, the other thing is now that thing is not an absolute value, it's a modulus. And you'll realize that, oh my gosh, that proof works fine for complex numbers. So you'd be bored to death if well, maybe I'll do a couple where I show that. Let me just do it. So an example might be, we know that the derivative of the product is F prime G plus F times G prime. Okay. And if you look in your freshman calculus book, you see when you calculate this thing, let's see, I'm dividing by Z minus Z naught. In your freshman calculus book, the classic trick is, okay, well, you add and subtract. Let's see, I'm going to subtract F of Z times, what do I do, F of Z naught times G of Z. And then I subtract it there, and I'm going to add exactly the same thing back, so I don't change anything. And now I've got to continue minus F of Z naught, G of Z naught, and I divide that whole mess by Z minus Z naught. And these are complex functions now, but now I realize, oh, I can pull that apart. That first piece, I can factor out the G of Z. And then I get a difference quotient in the F. And then in this other one, I can factor out an F of Z naught. And then I get a difference quotient in the G. So that's the times, that's the times. And you realize that as I let Z tend to Z naught, this is going. Well, let's see. I need to know something. I need to know that if something's complex differentiable, then it's got to be continuous. So this is going to tend to G of Z naught. This difference quotient is going to tend to F prime of Z naught. And this thing is a constant, so it's just going to sit there. And we have a rule about a constant times a function would be the limit of the constant times the limit. So let's see, this is almost a proof. Here's a fact. Complex differentiable function is continuous. So G C differentiable at Z naught implies G is continuous. By the way, in a freshman calculus book, I would need to do this step exactly like this. And it works out just fine. Let's see, why is that fact true? So by the way, this is the formula we're after for the product rule, and let me show you why this fact is true. The difference quotient, I like to use dq for that, is G of Z minus G of Z naught over Z minus Z naught. And that tends to, let's see, I'm going to write that as E of Z. Let's see, I'm going to write it as G prime of Z naught plus an error. Okay, the difference quotient tends to that G prime of Z naught, so that error goes to 0. Goes to 0 as Z tends to Z naught. Okay, so now if I solve for G of Z in that formula, I get G of Z when I solve for it is equal to G of Z naught plus G prime of Z naught times Z minus Z naught plus E of Z, the error, times Z minus Z naught. And now if I let Z tend to Z naught, this one just sits there, it's a constant. This one tends to G prime of Z naught, that's a constant, times 0, because the limit of a product is the product of the limits, and that's even more true here. E of Z tends to 0, and Z minus Z naught also tends to 0, as Z tends to Z naught. And so sure enough, we see that G of Z tends to G of Z naught. Check. And that's basically the proof you'll see in your freshman calculus book, in a careful book. Questions about that?
Okay, maybe it's not worth a drum roll, but now the thing we're going to talk about in this course for the rest of the semester are what are called analytic functions. F is analytic. Let's see. On an open set, it's critical that we're talking about an open set here. Analytic only makes sense on an open set. If it is complex differentiable at every point in the set. Okay, in Math 425 is going to be about analytic functions on domains. Connected open sets. Okay. Let's see, we have some simple examples of some analytic functions. Complex polynomials. Are analytic on the complex plane, on the whole complex plane. Rational functions are analytic where their denominators are not zero. Complex rational functions. Okay, that's an easy thing to check. Constant things are clearly analytic. Z is clearly analytic and its derivative is 1. And then you can use the product rule to do the same thing I did with that continuity. So it's a straightforward thing to check that from the basic facts. Let's see some examples. Let's write z squared equals x plus I y squared. Let's see, that's real part is x squared minus y squared, and the imaginary part is 2xy. When we look at analytic functions, it's going to be, we'll call this thing u of xy, the real part of the analytic function, and we'll call this thing v of xy. Notice how nice and smooth those functions are. Another example is e to the z, which is e to the x plus y, e to the x plus iy, and remember that was, the real part is e to the x cosine y, and the imaginary part is e to the x sine y. And this is a u of xy, and this is the v of xy. The question is e to the z analytic? I'm going to answer that question in the next couple lectures. But we have to think about it. I can't do like I did polynomials where I just say, oh, it's freshman calculus. I got to think about something outside of freshman calculus to do this problem. But I need more than freshman calculus. show it. The next question you might ask is something simple like z bar, which is x minus iy. Oddly, that x and y look like very nice things, so you think, sure, that's going to be complex differentiable, but in fact, it's not. So even though the u function and the v function are perfectly nice, infinitely differentiable in x and y, that thing is not complex differentiable. And let's see why not. Let's take the difference quotient at z equals 0. So that would be z bar minus 0 bar over z minus 0. Of course, that's z bar over z. I guess the easiest way to see this is not going to tend to something, is to write it in polar form. Let's write z equals r e to the I theta. And z goes to 0 exactly when r is small, when it goes to 0. Okay, so when I write it like that, remember this would be r e to the I theta bar over r e to the I theta. And remember, that's equal to r e to the minus I theta on top. And this would be r e to the I theta on the bottom. This is r's cancel, and I get e to the minus I 2 theta. That's not a single thing. So the limits are different coming in depending on the angle theta. So if you think about, here's the origin. If I come in along the real line, I would get e to the minus I 0 theta. If I come in along the imaginary axis, I'd get, let's see, that'd be pi over 2. I'd get e to the minus, I get something different. And in fact, I get something different from every possible direction here. So all these things would be tending to different things along these different rays. If I were to have done the difference quotient for z squared, those would all be going to the same thing. In fact, they'd all be going to 0. Remember, the derivative of z squared was 2z. And at 0, that would be 0. And so all those things would be going to 0, and that would make sense. This thing does not have a complex limit, because those things are all going to different numbers. And that turns out to be an important consideration when you're talking about complex differentiable functions. It's going to lead to something called the Cauchy-Riemann equations. So soon we'll see the Cauchy-Riemann equations, which means that the Cauchy-Riemann equations are pretty interesting. You would think you'd need to show that all those limits were the same from all directions. Turns out you only need to check the black ones, the real direction and the imaginary direction. If those two are equal, then everything's okay. And that'll come in the next couple lectures. Did I see a question back there? Yeah.
I'm confused. If the arrows all pointing towards the point, why is there no limit?
I'm going to calculate this limit sliding in along those directions. That would mean that r goes to